So I think now we understand how do we find the multiplicative inverses mod some integers. Just something before we continue is that this chapter contains most, definitions and things like that. So I try to give as many examples as possible to just make the, learning a bit faster and quicker. So I don't expect that you would remember all these definitions, but I would just provide enough examples that when you go back through them one more time, then I hope everything becomes more clear. So now that we understand that GCD and we can use that GCD to do the multiplicative inverse, so let's be a bit more formal over here. So there are some related problems over here that we can use same techniques to solve. We often have this equation over here that we want to solve, and particularly we are interested most of the time in cryptography when the value b over here is 1. And then what that means is that a times x becomes 1 mod n. That means that x and a are multiplicative inverse of each other. So that means that if a is co-prime to n, right? That means that the GCD of a and n equals to 1. Then we can use the extended Euclidean algorithm to find those integer r and s such that ra plus sn becomes 1. And then we can see that given this equation over here, we know that we can rewrite it that ra equals to 1 minus sn mod n. And this n, s times n divided by mod n, this would get canceled. So then it means that ra becomes 1 mod n. And this implies that r is the multiplicative inverse of a, right, mod n, just because of this relationship. And therefore, what we are finding x over here, x is just exactly our r that we found over here. So we can just replace it now. So for any equation, now every time that I say that we are working on mod n, find a multiplicative inverse, now we know the formula. We know how we proceed to find those things. We also have some other equations that are very interesting for us, and it is the kth root of some x that is, given this a and n over here, our goal is to find the x. So find x such that this equation holds. X to the power k is congruent to a mod n, right? So this is what we are interested in. And we would see in some situations, we call it the kth root of x, and then in some situation for a specific values of a, we have a very good and fast algorithm to find this kth roots of n. So I think the next two problems are quite clear. So sometimes we give some integer n, and we want to test if this integer n is prime or not. So we call it a primary test. Sometimes we have a integer n, and again we want to find the factorization of n. And we also talk about some discrete logarithm problems. So these are all has something to do with this modular n operation. So remember that on this discrete logarithm problem, we are given g, we are given y, we are given n, right? So all these values are given. The hard problem is to find x such that we can make this equality, right? And we discussed that this is going to be a difficult problem. How difficult? Soon we would have some proper slides to talk about it. Okay, this is one of the most important slides that we have for this specific page. And most of the time we talk about, we need a polynomial time algorithm. We need a polynomial time function. So we always talk about it. We never made it clear. So here we want to make it clear. So whenever we give an integer n, we can talk about two different things. Sometimes we talk about the value of n. So for example, I will tell you n equals to, 14. When I ask you about the value of n, then you would tell me it is 14, right? But sometimes I ask you about the length of n. And the length of n is 4. The reason for that is that I only need 4 bits to represent value 14, right? So 1110, right? This is in a binary format. So so the len, or this notation, is showing the number of the bits that I need to represent that number. So generally, the number of the bits we need to represent the value is the log of that value, floor of the log of value plus 1. And if you are, given the size of n, like if I tell you with 4 bits, what is the maximum value you can produce, then you can say that, 2 to the power 4. Maybe 16 is the maximum value that you can produce. So that being said, for now on, when we are talking about, we have a polynomial time algorithm, we are talking about the polynomial time to the length of these input values. For example, we say that there is an algorithm that we can do modular exponentiation. This is what we call it. You have some integer a, you raise it to the another integer b mod n. And we call this algorithm to be polynomially time computable. And then the complexity of this algorithm is depend on the length of a plus length of b plus length of n, where now we know that these values are the number of the bits that we need to represent any of these integers, right? So now it is understandable that it is polynomial. Actually, it is logarithm to with respect to the value of these values, because the number of the bits we need to represent n is just log of that value, right? So this is actually a sub-polynomial algorithm. So for example, sometimes we talk about an algorithm when the len of a equals to, len of b, and then this is equal to len of n. Sometimes we talk about the same numbers, and that is going to be 1,000 bits, right? So we want to see how quickly we can do this computation. So some heads up before we get to write down the efficient way for doing this computation. If I ask you to raise a to the power b mod n, what you can do is like you can do a times a multiply to a for b times, and then do mod n, right? So this is the naive way that you can do this multiplication. But the question is that before we see the algorithm, let's see if there is a better way to do this multiplication. Suppose I ask you to do a to the power 16. So my b is 16 here. Is there a better way to do this multiplication? So suppose I do a times a, so I get a2, right? If I raise this thing to the power 2, I get a4, right? And if I do that again, I get a to the 8. And if I just do it one more time, I get a to the power 16, right? So let's break this down. I did 4 times the squaring versus 15 times the multiplication in this naive algorithm over here. So you see that it looks like that there is a better way to do this multiplication. I don't have to, exponentiations, I'm sorry. I don't have to do 15 multiplication, just 4 squaring would be enough. Let's see another number. If I ask you to do a to the power 14, how can we do that? So let's see, how do I build it up? I do a to the power 2, and then I multiply this one to a, I get a to the 3, right? A to the power 3. If I multiply this to the power 2, a to the 3 to the squaring it, I will get a to the 6. And if I multiply to another a, I get a to the 7. And then if I raise the whole thing to the power 2, I get a to the 14, right? So you see that I'm doing, instead of 14 multiplication, I do 1, 2, 3 squaring and 1, 2 multiplication, right? So this looks like that it is a much better way to do the modular exponentiation. So here is the way that we would do it in most of the cryptographic libraries. So this is how the algorithm looks like. Mod power. So the input to this algorithm is some a, b, and n, and then the goal is to compute a to the b mod n. Okay. So we start by defining a variable, and then we let it to be a. Okay, we put a in y, and then we have a for loop. And then let me write it down and I explain to you. So what we start to do is that we are expected to have the binary representation of b. So we don't want to work with the integer b. We would have to have its binary representation. And it says that they start with the, whatever the length of the bit length of b is from another, skip the first index. And then you do a, you count down to 0. And then we want to change the value of y. So whatever the value of y is, you do the squaring, and then multiply another b if this bit location of b at index I is actually 1, and mod n. And then at the end, we will just return y. Okay, let me give you an example. This should make it clear. So suppose, this b, when b was 14, it was an interesting example. So suppose b is 14, right? So the binary representation of 14 is 1, 1, 1, 0, right? So the length of b, so we know that the bit length of 14 is basically 4, right? So what it says is that 0, 1, 2, 3, right? So start from over here. So in the beginning, I equals to 2. And what it's saying is that, and then, so let me actually put this one. In the very beginning, y equals to a. And then in the first loop over here, so we start with this bit over here, and then I equals to 2. And then what it says is that put in y, so whatever the value of y is, to do it to the, so y squared times a. And then what is the bit value of this position 2? So in the position 2, the bit value is 1, so to the power 1. This is equals to y so far is a, so I would get a squared times a to the 1, which would become a to the 3. Okay, and then we have this countdown loop, so then I becomes 1, so we are looking into this bit, 2, 1, and 0. So we are looking into this bit. So it says that y, again, set it to be y squared times a, and then what is this bit that we are representing, the location I, which is 1. So it is again 1. So what happens is that what is the current value of y? The current value of y is a3. So a3 to the power 2 becomes a6 multiplies to a1. This is going to be a7, right? And then we continue. With the for loop, I becomes 0. When I becomes 0, then this value is 0. So again, we would try to write the formula. So we said that y to the 2 times a, and then the bit at this location 0 that I is denoting is 0. So I would just do 0. And what would be the value? What is the current value of y? Is a7. a7 to the 2 is a14, right? Times a to the 0 is just like 1, right? So the result would be a to the power 14, right? So that's how we did the computation. And you see that no matter how large and these values are, of course, in every round, remember that we are doing mod n as well. So I think it should be clear now, right? So as you could see, instead of doing this tedious multiplication, writing a for loop for 14 times to do this multiplication, you see that we only run the for loop three times, right? Which is very amazing. It is the order of this algorithm is almost logarithmic to the length of or b, the exponentiation value. So this is our fast multiplication algorithm. So now you see that in cryptography, a lot of algorithms we talk about exponentiation, modular exponentiation. So now you see that we can do this computation very fast. Any questions so far? So the next one is something that it calls Chinese reminder theorem. It is actually a very interesting property. And so basically what it's saying is that if you have a solution of some value x over some different ni's, so we have m different n's that we every n is coprime to the every other n, ni is coprime to other nj, and then we can combine them together to find the solution of x mod I should say n1 times n2 times all the way to nm. Okay. So let me give you an example. Again, this kind of problems are easier to understand if we have an example. So suppose that I have m different m's, so n1, n2, and all the way to nm, and so such that every ni is coprime to the other n. So for those i's that are not correct to j, right, equal to j. For any, if you take any of these pairs, they're going to be coprime. That means that their GCD is 1. So now I would also define n to be multiplication of all these values, n1, n2, all the way to nm. So what we are trying to do is that given x given x the remainder of x with respect to every ni, so n1 r1 mod n1, x is congruent to maybe r2 mod n2, and so on so forth, to x is congruent to rn mod nm. Now what we are interested to do is to find x mod n. Okay. So the question is that, is there a way that we can, given the solutions of x with respect to any of this, decompositions, is there a way that I can combine them together to efficiently compute x? And the answer is yes. Let's start with an example. Suppose x is equal, the remainder of x is mod So I'm sorry, let me define my n equals to 528, and this is equals to 3 times 11 times 16. Suppose there is an x that becomes 2 mod 3. And then the same, this x becomes 5 mod 11. And this x is 3 mod 16. Okay. And then the question is find x. What is this value is going to be? Mod 528. Okay, so that is the question that you're interested to solve. So given this formula over here, so we have a specific, we are not interested in proving this. We just want to see the final computation, that it is indeed possible to do this computation. So we have some definition of capital Ni, and that is to be the multiplication of all n's except that n specific I. And so it looked like that the computation is going to be R1 and then N1 and then the inverse of N mod N and so on and so forth. So we have to combine them in this fashion so that we can find them. So then if I want to solve this, I can say that X equals to, for the first one, we say that the R1 is, if we look at the formula, it says that R1, N1, and then inverse of N. So the R1 is over here, 2 times N1. If we said that by definition, N1 is the multiplication of this entire N divided by this 3. So it's going to be 11 times 16. And then we're going to multiply this one to the inverse of n. So it's going to be 11 times 16, the inverse of these two values, not whatever the multiplication is, mod 3. And then I'm going to add to this R2, which R2 is this one, 5 times. So this is going to be the N2. So the N2 is multiplication of this 3 divided by 11. So it's going to be 3 times 16. And I'm going to take 3 times 16. I'm going to compute the inverse of this. Now we know the extended Euclidean algorithm. We can find this inverse mod 11. How do I know that I can find the inverse of mod 11? Because, well, 11 is an odd and prime number. So, of course, everything would be co-prime to this. So these are some numbers that I'm sure that we can find the inverse. And then for the last one is the R3. So we have R3 times 3 times 16. I'm sorry, 3 times 11. And then we're going to multiply this one to 3 times 11, the inverse, mod 16. Okay, and then I'm going to do mod 528, right? So if we do all this computation, I can find x mod 528. So, I was just given on some, residui of this n, and I can combine them using Chinese remainder theorem to build them up and compute that for n. So you might wonder, why would we need this one? Why do we bother to do this computation? So here is an example. We have a function size. Oh, yeah.
I am so sorry. I'm lost since a while, but I did not know when was a good time to interrupt. Can you go back to the thing we just did, the math? Okay, in this one, the 2, 5, and 3 come from where?
Oh, here. The remainder of x is 2 mod 3, 5. The remainder of x is 5 mod 11. And the remainder of x
Wait,
is
wait.
3 mod.
This 253, the remaining from what?
There is an x that we don't know, right?
Yes.
If we do x mod 3, the remainder becomes 2. So that is where we have the 2. We are given to these things.
Oh, we
And
were
then
given it.
we don't know the
didn't
x.
know.
Yeah.
We didn't
Yeah.
calculate that one somehow.
Yeah, as I said, these are given. So given these
Okay.
things, we want to find x.
And the second part where we were trying to find x, we did it with the Euclides thing where we break it up, right?
Yeah. So the inverse of this thing, we have to use that Euclidean algorithm to find.
Okay, and we did 2 times 11 times 16 because 11 and 16 is not the 3 on the mod.
Yeah.
And on the other primes.
Yeah, capital Ni, the definition is here. The capital Ni that you, for example, when you do R1 times capital N1, the N1 is defined to be your N divided by this N1. So you include all of those, other ones. For example, for the first one, my N1 is 3. So I just put 11 times 16. For the second one, you would put the other 2, but you would not include 11. And for the last one, right, so you put 3 times 11, but you would not include this one, right? Just like what this capital N formula is saying over here.
Okay. Yes.
I mean, it doesn't work to really go and prove this. It's just like some computation. Now, I think you will understand the value of, why do we have to bother us to do this computation. So there is a isomorphism. Yeah, you're welcome. There's an isomorphism relationship over here, and we have this psi function that can take an element from Zn, and it can map it to elements of n1, n2 to nm. So suppose that, let me give you an example. Suppose that your Zn, we know that this is a set of elements from 1, 0, 1, 2, all the way to n minus 1, right? So we know that these are the elements. And suppose my n, I can write it down as p1 times p2 times all the way to pk, right? I can write it with these things. It doesn't have to be a prime, just decompositions. And then what this psi is saying is that it takes an element from Z, and then he would compute the X. Let's say we choose the X from Zn, and then you compute X mod P1, X mod P2, and all the way to X mod PK, right? So what it is saying is that it takes an element from n, Zn, and then it would just, do the, compute the X mod P1, P2, P3, and so on and so forth. So now we represent this one as a tuple, right, of some smaller integers. So let me give you actually a very small example over here. So we are talking about the psi function, and suppose my n is 15. So my z15 is actually numbers from 0, 1, 2, all the way to 14. So I know that I can write 15 equal to 3 times 5. So this means that for any x from z15, I can map it to x mod 3 and x mod 5, okay? Because n is 3 times 5. So let's take some examples. What 0 would get mapped to according to this? So 0 mod 3 is 0, and 0 mod 5 is just 0, right? What 1 would map to? 1 mod 3 is 1, and then 1 mod 5 is again 1, nothing interesting. 2 would get mapped to 2 and 2 again, because the mod doesn't change anything. And here comes the interesting part. When you take integer 3, you compute 3 mod 3, it would become 0. And then 3 mod 5 again becomes 3, right? And if you continue and do for 5, for example, you get 5 mod 3 is 2, and 5 mod 5 is 0, right? So you see that we are taking these integers and we are mapping them into 2 different integers. Well, okay, I know you're a bit lost at why do we do that. I think now it would become interesting. So suppose that my n is, it's I can decompose it into 2 big primes, p and q. Then according to this phi function, I can rewrite any x from this zn into x mod p and x mod p. So basically, we would take an element and it would map it to zp and zq. So this means that, what would be the application of this? Why do we bother to do this, mapping? So the application is over here. Suppose that we want to do this modular exponentiation. We have some a, we want to raise it to the power b mod n. And suppose our n is huge, it's a very large number, it's very, very, very big. So one way that we can do the computation a bit more efficiently is that we can break x into, suppose that I know the p and q. I can take this x1, I can do this computation mod p, and I can do, a to the b mod p, and then I can do a to the b mod q. And then using the Chinese remainder theorem, I can combine this x1 and x2 to compute x mod n, right? So that would be the application. How so? How does it help with the application? Suppose my n, the length of my n is s bits, right? So when we compute p and q, we normally choose 2 p and q that they have almost the same amount of length, bits. So then it means that the length of p is equals to length of q almost equals to s to the half of those bits, right? So s to the 2, because if you multiply these two p and q that they have this many bits, then the result would be s bit n. Okay. So, and now suppose we have some computation, we do some computation that the order of this computation, the complexity of this computation is the cubic, s cubic. So, to the length of n. And if we follow this idea, we do this psi, we use the psi to map it to, mod p and mod q, then what we are doing using this idea is that, so for the first one, because the p is only s to the 2, then the computational complexity of applying that operation on that is just s to the 2 to the 3. Plus, the same thing applies for the q, right? So overall, our computational complexity is just, we get a significant cut on the number of the, for loops that we need to write to do the computation. So that is the reason why we do this computation. So in some RSA, example is like in the RSA computation, sometimes when n is huge, we use this idea to break, the computation into a smaller chunks, and then using Chinese remainder theorem to combine them together. You may say that, well, Chinese remainder theorem, the previous page, also would have add some computation. What is the real benefit on that? So I got to say that, sometimes the computation is not the only thing that matters. Imagine you are working on an IoT device that you have a very small amount of memory. So you can just go ahead and do this computation right away on your device because your device doesn't have enough memory to do it. But applying this idea, you will cut the memory space that you need into half. right? So you can just do one of this computation, and then you keep the result, and then you do the other half. And that would really help you in a lot of scenarios, especially for those credit cards when they want to do the computation. They can save a lot of memory. But I got to say that for the today's CPU and the smartphone that you have, we would barely use this optimization. But this is an optimization that you can remember in some scenarios when you're going to work with some extremely restricted devices. Okay. I'm just going a little bit fast today, and the reason is just because these are mostly definitions. There are not much things to discuss. The places that we can discuss, I'll pause and we could have enough discussions. And if you think you have any question, please feel free to stop me. I'll be happy to explain more. So I think this is a part that we spent quite some time in the previous lecture, and then we talk about what is a group, what is the operation, what are those properties that we need to form a group. And beside that we said that these 4 are essential, but now we start to add some other properties that, if, for example, x this operation y equals to y this operation x, for example, you always say x plus y equals to y plus x, right? This is very easy to understand. And addition, under integers, because we have this property, then this group of z or zn are abelian, or we call them commutative. But a lot of cases this is not obvious. For example, let me give you another example. Suppose I define S to be a set of matrices A, B, C, D, right? So this is my matrix, such that A, B, and C, and D are in Z. And the operation is multiplication. So we know that in integers, all of them are commutative. This is very obvious operation. But how about the matrices? Do you think that if I take 2 matrices, A, B, C, D, and then I multiply this one to E, F, G, H, this is going to be equal to E, F, G, H times A, B, C, D, right? Obviously, this is not the case because, matrix computation, they cannot, the operation over matrices are not commutative. That's what we are saying, because you cannot, swap your elements and expect to get the same result. So, we just take this as granted because a lot of, set of integers, when we do addition, multiplication, division, all these things, the results are the same. So we always imagine that all the groups must be commutative. But this is a small example, counterexample, I would say, that show you that this is not the case all of the time. You need to be careful about it. So these are some examples of groups. So we said that the set of integers and the operation is plus. This is going to be a group. We have, if we have a closure, because any 2 integers you take, you add them, you get another integer. You have identity element, which is 0, E equals to 0. And the inverse of A is minus A, right? So this group is an associative rule is there. So it is okay. It is a group. And then the set of rational numbers. So this is also a group. So the set of rational numbers, remember that it is some A and B, such that A and B are in Z. So this is a set of rational numbers. So we know that this is also going to be, the operation is multiplication. We know that this is also a group because if you multiply any of this AB times CD, it would become another element in this group. The identity E equals to 1 in this group. And if you want to find the inverse of A over B, it is going to be the inverse of this one is just B over A, right? Because A times B times B times A is going to be B. which is equal to 1, right? And so on and so forth. And another example are Zn plus, so the set of integers that are less than n, and the operation is modular n, and the operation is addition. So, and again, we've practiced this one, and we know that this is going to be a group. Another one is a set of multiplicative inverse, a set of Z star n, and this is a very interesting one. So you see that they are very similar to each other, but remember that it contains only those set of those values that are the GCD of them is just 1 to n. So the values that are co-prime to n. Let me give you an example. If you're talking about Z5, so your values, the elements are going to be 0, 1, 2, 3, and 4, right? So if you're talking about the Z star 5, you're talking about the elements that they have inverse. So we are only having 1, 2, 3, and 4, right? So 0 is missing. And the reason for that is that 0 does not have multiplicative inverse, right? 0 inverse, okay? And then beside that, we have a notation of polynomials, you know, that with this notation, it means that we have a set of polynomials that we can add polynomials or subtract polynomials, and the coefficients are from Z. So for example, minus x6 plus, I don't know, 11 x4 minus 9x3 plus 1, right? So you see that all the coefficients are from Z, right? So they are belong to the set Z. And then we use the variable x to represent this polynomial. So if I have two polynomials, I can add them together because, you know, when I add these things together, you know, the coefficients are in Z. So, you know, the result would be, again, the coefficient would be somewhere in Z. So I don't have to have only integers. I can also have polynomials that hopefully soon we would get to there. All right, I think we are close to your the break time. So how about we take 10 minutes break and then we come back.